let me start out as always by asking you to do a few examples which will help us to orient ourselves in terms of the concepts that we are studying. Okay, first one is an example. I'm going to give you a transfer function which is a rational transfer function. The general form is a naught by b naught. These are constant. The numerator terms, which are the zeros, k equal to 1 through m, 1 minus ck z inverse, divided by the denominator are the poles of the system, k is equal to 1 through n, 1 minus dk z inverse. Okay, so let's write down. We have a transfer function which has got zeros at z equal to ck and poles at z equal to dk. Okay, in this case, k is equal to 1 through n, the other case k is equal to 1 through m. All right. Now, here is a set of important results which come from the properties of Z transform. If h of n is the underlying time domain sequence which has the Z transform h of z, then what is the Z transform of the sequence h conjugate of n? Okay, and you can verify that this will be h conjugate of Z conjugate. That will be the response of the system with the which corresponds to h conjugate of n, and h conjugate of minus n, time reversed and conjugated sequence. Okay, we saw this in the context of the magnitude squared response. This will have a Z transform which is given by h conjugate 1 by Z conjugate. Three important cases that we have obtained. Okay, now let us look at the corresponding transfer functions. So this is h conjugate of n. We got a Z transform which is given by h conjugate Z conjugate. Now I want to know where are the zeros and poles of this transfer function which correspond to the Z transform of h conjugate of n. So no problem, we will compute it. You get a naught conjugate divided by b naught conjugate. When you conjugate h, these will get conjugated. Then where are the pole terms? K equal to 1 through m, 1 minus ck conjugate Z inverse. Okay, make sure you are getting the correct substitution, and there are two conjugations, so therefore the Z conjugate will become Z itself. Okay, denominator will be k equal to 1 through n, 1 minus dk conjugate Z inverse. Okay, important. So where are the zeros? Zeros at Z equal to ck conjugate. More important, where are the poles? The poles are at Z equal to dk conjugate. Okay. In terms of region of convergence, both h of z and h conjugate of Z conjugate will have the same region of convergence. Why? Because both have got the same pole locations, same pole radius. They are at conjugate location, does not matter. So in terms of the radius, you can get the same. So that an important aspect. Okay. Now comes the h conjugate of minus n. This will have h conjugate of 1 by Z conjugate. Take a minute to write this down. A naught conjugate divided by b naught conjugate. What is the expression that we get? Pi k equal to 1 through m product 1 minus ck conjugate Z, not Z inverse, Z. Okay, that's because of the 1 by Z conjugate. The denominator will be pi k equal to 1 through n 1 minus dk conjugate Z. Okay, where are the poles and zeros? The zeros are at Z equal to 1 by ck conjugate, reciprocal conjugate location. And the poles are at Z equal to 1 over dk conjugate. Okay. Good. Now, why did we do all of this? For a very important task. Okay, if h of z is LTI. That means it has got impulse response h of n, which is causal and stable. This LTI system is causal and stable. Then which of the following, I'm going to give you 3 cases, which of the following systems are causal and stable? Causal and stable. Okay. Important thing to note, causal stable means all zeros, or zeros can be anywhere, poles have to be inside the unit circle. So that's the key. Okay, first quantity that I want you to evaluate is a transfer function that is given by h of z, h conjugate of z conjugate. Okay, where are the poles? If the poles are at z equal to dk, for this the poles are at z equal to dk conjugate. So causal and stable means greater than the largest radius of the largest pole. So no problem, h conjugate of z conjugate will also allow you to satisfy. So g of z will represent a causal stable. It can satisfy the conditions for causality and stability because all the poles are at the same location as h of z, which is which is already given to us as causal stable. Okay, second term, g of z is equal to h of z inverse. H of z inverse. Okay, so which then says that the poles are at z equal to 1 by dk, reciprocal. Okay. If the original transfer function h of z had got poles inside the unit circle, now h of z inverse is going to have poles outside the unit circle. So what you will have in this particular case, if you insist on causality, okay, then what will happen? You will have to take ROC outside of the largest radius, which means that it will not include the unit circle and therefore it will be unstable. Okay. On the other hand, if you are willing to allow it to be non-causal, then it can be the radius region of convergence less than the minimum radius, and therefore it can be causal. So it can be non-causal and stable. What will be the ROC? Mod z will be less than the minimum radius of 1 by dk, k equal to 1 through n. So notice that tying it into the notions of causality and stability must be very important. You should know how these are going to be related. Okay, last one, g of z is equal to h of minus z. Okay, what about the transfer functions? Just to note, this corresponds to a time domain sequence which is given by an exponential sequence minus 1 raised to the power of n times h of n. Okay, again, that doesn't matter. For us, we want to know where the poles are located. So we can easily verify that the poles are now located at z equal to minus dk. Okay, which means that in terms of radius, same radius, so therefore you can have this system can satisfy causal and stable. Okay, I hope you are comfortable with it. Important to be able to apply these concepts and be comfortable in terms of the interpretations. All right. Now comes a very familiar example which we have seen multiple times. We're going to see it one more time. This is the moving average filter. Moving average filter with n equal to 8. Okay, if I were to ask you to write down the impulse response, this will be an impulse response which starts at time n equal to 1 and has got 8 taps of equal height. Okay, and the last step will be at, so this starts at 0, ends at 7. All of them have got the same height equal to 1 by, you can write it as 1 by 8. Okay, all of them have got the same height, or you can write it as 1. Just 1 by 8 is just a scale factor. So the impulse response h of n is equal to 1 by 8 times u of n minus u of n minus 8. Okay, I hope you are comfortable with that. Okay, now if you are interested in sketching the magnitude response, then what you would do is compute the dTFT, He of j omega. Okay, this will be summation n equal to 0 through 7 e power minus j omega n. There's a scale factor of 1 by 8. You can, make sure you don't leave that out. Okay, so this will be 1 by 8, 1 minus e power j 8 omega divided by 1 minus e power minus j omega. Okay, you can write this as 1 by 8 e power minus j omega 7 by 2, 3.5. Basically, when you factor it out, numerator will be sine 4 omega divided by sine omega by 2. Okay. Notice that the numerator will go to 0 whenever omega is pi by 4, pi by 2, 3 pi by 4, all the multiples of pi by 4 will go to 0. Okay, that's an important aspect. Now, you can either get it from the expression for He of j omega, or you can also do Z transform. What you have here is 1 minus Z power minus 8 divided by 1 minus Z inverse. You can solve for the numerator. Numerator says that there are 8 zeros uniformly spaced around the unit circle. Okay. Uniformly spaced around the unit circle. So let's mark them. 1, 2, 3, 4, 5, 6, 7, 8. There's a pole at z equal to 1. So therefore, there is a pole here. There's a pole 0 cancellation, which then leaves us with 7 zeros around the unit circle. Okay, why are we studying this? Now, using the principles of what we have studied in terms of the magnitude response, can you now help sketch the magnitude response of this particular transfer function, where there are 7 zeros are uniformly spaced around the unit circle except at omega equal to 0. Okay, so at omega equal to 0, you are not very near to any of the zeros. You start at some gain. Okay, let that gain some arbitrary value. Then as you approach the first 0, the transfer function goes down to 0, then starts to increase. The next 0 comes uniformly spaced, then another 0. You see, there are basically 7 zeros. So 1, 2, 3, 4, 5, 6, 7 zeros are present, and then goes up again. Okay, so basically you come back to this. So 1, 2, 3, 4, 5, 6, 7. Yeah, no, I think I made 1, 2, 3, 4, 5, 6, 7. Yeah, okay, I drew one extra. Okay. This is the magnitude response. I hope you are comfortable with this particular interpretation and saying that, okay, so this is a low pass filter. Where is pi? Pi is situated here. What are these frequencies? This is pi by 4, this is pi by 2, this is 3 pi by 4, all multiples of pi by 4. Okay, so and this will be 7 pi by 4, and here is 2 pi. Okay, so this is a low pass filter. Now, just so that you are comfortable in visualizing it, supposing there was a pole 0 cancellation which cancelled out this 0. That means there is no 0 there. Okay. Can you now sketch what the modified magnitude response is going to be? Okay. So it will start out here. You will see, I'm going to draw it in red. I'm just going to draw it slightly shifted, but you can see the two graphs. The first 0, second 0. Now, there is no 0 at pi. So, then what happens? The magnitude response will go up, right? Basically, it goes up. And then it will come down again at this point, go up, come down, go up, come down, and go up again. Okay, so basically you can see how the absence or the presence of a 0 can make a difference in terms of the magnitude response. This of course is not a low pass filter or a high pass filter. It's basically a combination. It's allowing low frequencies and high frequencies. It is removing frequencies in the middle, so you can think of it as a band stop filter, something like that. But more important, how the removal of a 0 affected the behavior of the system. Okay, I hope you are comfortable with that. Now, with this background, we are ready to make some important statements. So, here are some statements regarding the relationship between the magnitude response and the phase response. Relationship between the magnitude response, this is magnitude He of j omega, and the phase response. And this is argument of He of j omega. Okay. First and foremost, these two are quantities that are derived from the underlying sequence. However, if you know one, you cannot guess the other because both are independent pieces of information about that. So, we have He of j omega, which is magnitude He of j omega e power j argument He of j omega. Okay, so one broad statement is the magnitude response does not provide information about the phase response or vice versa. Okay, magnitude response does not provide information about the phase response and vice versa. Why phase response does not give information, okay, in general, vice versa. Okay, but the second statement is going to be very important. Okay, if we know the magnitude response, if the magnitude response is known, or for example, the magnitude squared response is known. Okay, if this is known and we know the number of poles and zeros, number of poles and number of zeros are known. Okay, this is exactly the magnitude squared response. So, you know where the poles are, where the zeros are, how many of them are there. Then there are only a finite number of choices, right? You know how many transfer functions you can get, and there are only a finite number of choices for the phase response. Depending upon which combination of poles and zeros you have taken, finite number of choices. It is restricted for the phase response. Okay. And you can actually restrict it even further by imposing additional constraints. Additional constraints. What are some additional constraints which can limit the number of choices for the phase response? You can say that you want causal stable. That is one. You can say that you want real coefficients. Okay, and you can also say that you want to have minimum phase lag. You want all the zeros inside the unit circle. Okay, there are these conditions that can be, you can put on, which will limit the number of choices that you have for the phase response. So what are we saying? In general, I have a sequence h of n for which I have computed the dt of t. There is a magnitude response and then there's a phase response. Typically, you will have to study both of them together. Independent information is coming from both of them. However, if you know the magnitude response or the magnitude squared response and you happen to know the number of poles and zeros, then what we have is only a finite number of choices that you have for the pole and zero combinations. And that means the number of choices is limited to a finite number based on the choices that you make. Now, in addition, if you can impose certain other constraints which will reduce the number of choices, then you eventually may be left with just one or possibly two possible sequences. All right. So I hope you are comfortable with this particular aspect. And what I would like to do is now build on the sequences that we are going to be looking at, and look at it in a very careful manner. Okay. So here is a statement. Okay, a minimum phase lag system. So this is a statement. Minimum phase lag system or transfer function h of z. Okay, which is causal and stable. Causal and stable. What does it mean? It means that it has all poles inside the unit circle, all poles inside the unit circle, all zeros inside the unit circle, because that is what will give you the minimum phase lag inside the unit circle. Now, a minimum phase lag system which is causal and stable satisfies the following conditions. Okay, it of course has minimum phase lag. It has minimum group delay. We showed that using the property of an all-pass function, and it has what we call as maximum partial energy. Okay, we are going to see that. I'm going to give us some very important and interesting insights for us in terms of our understanding of the discrete time systems. Okay, so here is the important consideration.